Welcome, chemistry students. Today we're going to look at how to do some basic stoichiometry calculations. So first off, what is stoichiometry and why is it useful? Well, stoichiometry is this idea of being able to convert between one substance and a different substance within a chemical reaction. So this is related to mole conversions, but it's taking it to the next level. So it's a way for chemists to convert from one chemical substance to a different substance within a chemical reaction. Now, this is extremely useful to scientists. This is like the main idea of like a first semester chemistry curriculum, right? This is what we can do. This is how the math and chemistry come together. This is the idea of if you get into a car accident and your airbag inflates with a certain amount of air, there could be a reaction that produces just the right amount of air to inflate that bag perfectly. This could be how you design different fuels, burning things and making sure that you're generating the right amount of energy as a final product. It's all this idea of doing the conversions for chemical reactions. Now, when you're talking about doing conversions and setting all these calculations up, the first step to every stoichiometry problem has to be a balanced chemical equation. So you're always starting with a balanced chemical equation. So this one says the combustion of gaseous ethane, which is dicarbon hexahydride. So carbon, di is C2, hexa is 6, so C2H6, it says it's a gas, so I'm going to put a little G in parentheses. We know that combustion reactions always involve a reaction between a hydrocarbon and oxygen gas. And we know oxygen is one of the 7 diatomics, so it's going to be listed as O2. And then combustion reactions always form the same products. They always form carbon dioxide, CO2 gas, and water vapor, H2O. Now, combustion reactions are always exothermic, so they're always going to generate energy as well. So in a thermochemistry unit, you might go into details for the energy component as well. Now, to balance this chemical reaction, I want to get the same number of elements on both sides. So I can see on the left side, I have 2 carbons. On the right side, I could put a 2 in front of the CO2. On the left side, I have 6 hydrogens. I'm going to put a 3 in front of the H2O on the right side. On the left side, I have 2 oxygens. On the right side, I have 2 times 2 is 4, plus 3 times 1 is 7, which means I'm going to need a 3.5 as my coefficient for my O2. Generally, it's not accepted in a high school level to leave it as a decimal form. In college, you can do that, or AP chemistry, you can, but in a general level chemistry class, typically you don't want to leave fractional coefficients. So I'm going to go ahead and double everything just to get them to be whole numbers. So I'm going to multiply all my coefficients by 2 so that they're all whole numbers. So I get 2746. Now, those numbers are going to be what we use in a mole ratio. This is going to be the new step that stoichiometry includes that a basic mole conversion problem would not. So I did them in a different color specifically because I'm going to reference them as we go throughout these practice problems. So the first one here is an example of an easy problem. This is about as simple as it gets. There's relatively few steps here, and it's not going to ask us to do any additional conversions other than moles. It says, if you react 0.928 moles of ethane, so there's my given, how many moles of O2 are required? So I always start off with my given over 1, 0.928 moles of C2H6 over 1. And I'm going to use a conversion factor to cancel out those moles of C2H6. So if you're familiar with mole conversions, this is going to look familiar so far. The new part is that I am going to convert directly into moles of O2. So by creating a ratio between the moles of one substance and the moles of another, this is called the mole ratio, and these numbers come from the coefficients in my balanced equation. That balanced equation represents the proportionality of how much of each of the reactants are going to be reacting and how much of the products we're going to be making. So if I look at my coefficients for O2, for every 7 moles of O2, you need 2 moles of C2H6. So a 7-to-2 ratio, and it comes directly from those coefficients. So I'm always looking back at my original balanced equation to get those. Now it just becomes a straight up conversion problem. If I take my calculator, I take 0.928 times 7 divided by 2. I get 3.248. My given started with 3 significant figures. Mole ratios have an infinite number of significant figures, so I don't need to worry about those. So my final answer is going to be rounded to 3.25 moles of oxygen. That would be my final answer, 3 sig figs for how much oxygen is required to react that amount of ethane. Now, the way that you make these problems harder is by adding more steps. That's a common theme in chemistry. The easiest problem has the fewest steps. The hardest problem is going to have more steps. So these next two are considered medium difficulty problems, and they're just adding an extra step using molar mass as a conversion factor. Now, the first one gives us an initial number, 79.8 grams of carbon dioxide, and then it's asking for how many moles of water will also form. So I'm looking back at the same original balanced equation. I can tidy up these arrows here, so I'm just looking back at the original equation, but I'm always going back to the original equation. Now, this mole ratio is my new step, but it's called a mole ratio, which means I always have to get whatever my given is into moles. So my first step here is I want to get into moles of carbon dioxide, and I'm just going to use the molar mass. So if I add up carbon dioxide, carbon's 12.01, oxygen's 16, so I get 44.01 grams of carbon dioxide for every 1 mole of CO2. Now I can cancel out grams, and I'm in moles of CO2. So here's where I can then cancel moles of CO2 and convert directly into moles of H2O. This is that new step. This is my mole ratio. And for the mole ratio, we're always looking back at that original balanced equation to get that ratio. The coefficient for H2O is a 6. The coefficient for the CO2 is a 4. You never simplify it. I don't have to worry about simplifying that to 3 over 2. I just leave it. It makes it simpler when I'm looking back and checking my work if I make a mistake. And your calculator will do all the work to simplify it. So now all I have to do is type this into my calculator. My 79.8 started with 3 sig figs. 79.8 divided by 44.01 times 6 divided by 4 gives me 2.719. I'm going to round that to 3 sig figs to be 2.72 moles of H2O. So that mole ratio converts us. Don't worry about sig figs for molar mass or mole ratio. I just go based on the original number that was given. Question C is the same problem, except it does the mole conversion at the end. So it doesn't matter what order we do these steps. I'm given an original number of moles of ethane, moles of C2H6, and then it's asking me to solve for grams of CO2. Well, I'm in moles, so I can go straight to my mole ratio right away. I can cancel out moles of C2H6 and convert into moles of CO2. So it's the same idea as what we just did. I'm going to be looking at my mole ratio from the original balanced equation. So I go back up to the original balanced equation, and I want to find the coefficients for CO2, which was a 4, and the coefficients for my ethane, C2H6, which was a 2. Don't bother simplifying it. I just leave it exactly as it is. But this problem is asking us to solve for grams of CO2 at the end. So now I'm going to add my molar mass as my final step. 1 mole of CO2. We already did the math in the problem above, was 44.01 grams of CO2. In my calculator, I type it in just like before. 1.298 times 4 divided by 2 times 44.01. Now my given started with 4 significant figures. So now I'm going to write down the first 4 digits. So 114.2. 114.2 grams of CO2 is my final answer. So I'm always matching the number of significant digits in that original number that we started with. Now, the last 2 here, I would say, are the more challenging. These are the harder versions of a basic stoichiometry conversion. And all they're doing is just throwing in other conversion factors. Now, a gram to gram conversion just requires us to do an extra molar mass conversion. We're starting with something in grams, and it's asking us to solve for a final answer that's also in grams. The problem is the mole ratio always has to be in moles. So it's just adding on to the work that we're doing. So I'm going to start off with my given, same as before. I'm always following this kind of same formulaic process. Start with my given, and I always need to convert it into moles. So I'm going to go 1 mole C2H6. Carbon's 12.01 times 2 plus 6 times 1.01. That gives me 30.08 grams. Now I'm in moles of C2H6. Now I can use my mole ratio to cancel moles of C2H6 and go directly into moles of O2. To get those numbers, I'm always going back to the same original balanced equation. Now, different problems, you use different balanced equations. If it gave you a brand new problem, you'd balance that equation first before you plug it into this. So my ratio is a 7/2. 7 O2s for every 2 C2H6s, ethanes. Now, this one was asking me to get a final answer in grams, so I'm going to add one final step here. 1 mole of O2 is 32.00 grams of O2. My given was 50, which is only 3 significant figures. So 50 divided by 30.08 times 7 divided by 2 times 32 gives me a final answer of 186. I'm going to keep just those first 3 digits. 186 grams of O2 is my final answer. Double molar mass conversion there. So again, we're just adding steps to make these problems more difficult. Now, we're not limited to just mass. Mass is the most common conversion we do. Again, in a chemistry class, typically you have access to a balance, which makes grams the easiest thing to mass or to record when you're doing laboratory experiments. But we can do other things. You are not limited. You could use density. You could use molarity. You can use Avogadro's number. So this one shows us one where it's asking us to solve for a final answer in molecules. So this is where Avogadro's number comes in. So I'm going to start off with my given 72.0 grams of oxygen. And again, I'm always getting into moles. I always want to go to moles first. So 1 mole of oxygen is 32.00 grams. Once I'm in moles, then I can set up my mole ratio. I'm trying to solve for CO2. Again, this mole ratio, converting from one substance in my balance equation to a different substance in the balance equation, I always go back, use the coefficients from that balanced equation. So I'm going to be looking at a 4 and a 7. So 4 CO2, 7 O2s. Then my last step here, instead of looking up the molar mass of carbon dioxide, it wants to know how many molecules. Well, for every 1 mole of CO2, we have 6.022 times 10 to the 23rd molecules. This is Avogadro's number. So when I do this conversion now, again, same 4 steps along, I'm just going to type in 72 divided by 32 times 4 divided by 7 times 6.022 second comma E23. I like to use the scientific notation built into my calculator. I get this number. I'm going to round it to same 3 sig figs that I started with in my given. So I'm going to have 7.74 times 10 to the 23rd. 7.74 times 10 to the 23rd molecules of CO2. So I follow the same sig fig rules. I'm just using whatever conversion, whatever molar conversion I need for that particular problem. As you progress to more difficult stoichiometry conversion problems, you're going to see other units thrown in there at you, but you follow the same basic formula every time. Get your given into moles, use your balanced equation to figure out the mole ratio, and then convert whatever moles of your product or whatever answer you're trying to look for into the appropriate units. Hopefully you found this video helpful. Good luck on all of your future conversions, and thanks so much for tuning in.